Hi, this is Mike Mulholland, and today I'm going to be talking about the side-side angle potential congruency rule for triangles. So this video is rather long, but if you like geometry, then I think you'll enjoy it. I hope you'll watch it. And I submitted this question because I had worked out detailed answers for myself, and I wanted to share them in case other people were interested. So here's the question. Explain side angle potential congruency rule for triangles. It's not one of the congruence rules for triangles, but there are conditions under which it does guarantee congruence, including hypotenuse-side. So that's what we're going to be exploring. And it's a sequel to my video answer to explain triangle congruency rules. Near the end of that video, we showed this illustration of two fixed sides and one fixed angle adjacent to only one of those sides, resulting in two different triangles. The red sides are the fixed sides, and the angle with the red dot is the fixed angle. And in that video, we came to these conclusions. Two fixed angles define the shape, but here we only have one fixed angle. Adding two fixed sides is not enough to reliably define the shape when only one of the fixed sides is adjacent to the fixed angle. So either fixed side would be sufficient to define the size of the resulting triangles of the same shape, but since we can have two different shapes, this does not reliably produce congruent triangles, so it's not included in rules of congruency for triangles. But we're going to explore that further. So from here on, we're going to use some standard geometry symbols that I didn't need in the previous video, like the line over it, that means the line segment. Without the line, it means the length of the segment. That means angle XYZ, with Y as the vertex, formed by points XYZ. And measure, or M in front, means the measure of that angle. So typically listed illustrations of congruence rules for triangles include something like those two end results above, and say that thus you cannot use side angle to prove congruence. And they often include a diagram like that one below to show why there's two possible shapes. This one continues the color scheme I've been using for black for unfixed and red for fixed. So here's our fixed side and our fixed angle, unfixed side, and then two possible locations for the fixed side that's not adjacent to the fixed angle that work. This arc shows possible locations of vertex A and where this line, so vertex A has to be on this line because that angle is fixed, and has to have this length for side AB. They meet here, but they also meet there, so we get two possible triangles. And side angle explanations usually go no further than that. But it turns out that triangles with equal values of side angle will always be congruent when certain additional requirements are met. Those requirements are usually not explored or even mentioned because they split side angle up into subcases based on additional information that often won't be given or able to prove, and they're more complicated than what we've considered so far. So we're going to explore those subcases, mostly because it's interesting, but also to explain the one common rule for proving triangles congruent that we haven't come across yet in the other video. So we're going to explore the effects of varying the relative lengths of the two fixed sides, which we'll do by varying the length of one while holding the length of the other one constant, and then exploring the effects of varying the fixed angle. So we're going to vary the length of the fixed side not adjacent to the fixed angle. And in this diagram, we're going to consider first having the line having the side having the length shown in the green scenario, which is like what we just saw before, and then making it shorter. So as we go to the yellow scenario, if the line is shorter, the possible points for vertex A get closer together, and the shapes of this triangle versus this triangle are a little bit closer. And then when you get to the red scenario, if you go as far as possible, this is the shortest possible length of side AB that still works with this fixed side and that fixed angle. When you get to this point, this arc that shows the possible the length of side AB is tangent to this line and touches it at only one point, and that would be perpendicular. That would be a right angle. So here we have only, under those circumstances, only one triangle is possible. But we don't need a new rule for that because we have an additional angle. So we now have two fixed angles and two fixed sides. If we use just either one of those sides, we could go angle, angle, side, or we could go angle, angle, side. And so we don't need a new rule. We just need to recognize that under these circumstances, there's a rule that's already accepted, already known, that we could invoke. Now let's do the opposite. Let's now let's consider having this side have the length shown in the yellow scenario and make it longer and longer and see what happens. So we make it a little longer and we get to the green scenario where you've got this triangle or this triangle. Now, what about the blue scenario? In the blue scenario, this length for side AB is the same as the length of the other side. So this triangle works, but over on this side, vertex A and C would be in the same place, and that doesn't work. So that's a boundary for getting two triangles or getting only one, where side AB is as long as this, or in the purple scenario, even longer. So over here it would be like that, which doesn't work. So if side AB is as long as or longer than side BC, you're only going to get one triangle and congruence is assured. And this is just spelling out what I just said. Now let's look at what happens if we vary the angle instead. So what we have here, this is the perpendicular is what we saw when actually the shortest possible length of a side that could work, and it bisects the other possibilities. Like here and here, this would, if we had a length like that, then that would work and that would work, and this would be exactly in the middle. And same here and here. So we see a trend that it's less and less likely that you're going to be able to fit in something in here for a side. Lots of room up there. So when we get to the purple scenario, the bisector would be here, which means that nothing is possible on this side, only on this side, and only one triangle would be possible. And that's what I just explained. So congruence would be assured when the angle is 90 degrees. Now, what if it's more than 90 degrees? Here, the vertex, in the purple scenario where it's 90 degrees, vertex A could be anywhere along here, but there's only one possible triangle for any length of this. Whatever the length is, you get where it hits here, and there's one possible triangle. And the same if it's more than 90 degrees. Whatever the length of this given side is, you figure out, okay, where will that hit over here? And that makes a triangle that has to be a certain shape. And you don't get this two possible triangles bit, you only get one possible triangle. So now we can see it's not just where the measure is 90 degrees, it's where it's greater than or equal to 90 degrees, that there's only one possible triangle. And so that would prove congruence under those conditions. Now, how do we know, how can we prove for this side being longer than that one that, or how can we prove that this has to be longer than that one? Since we already established before that when it is longer, you've only got one possible triangle, but how can we prove that this has to be longer? At a glance, you can see you got two legs here, and that's the hypotenuse. The hypotenuse is always the longer side. But there's a better way to go because it takes care of not only this, the purple scenario, but also the orange. And that is that this angle here, this given angle, when it's 90 or more, it has to be larger than both of the other two. Even if one is 1 degree, then the 1 degree, the other one would be 89 degrees. If this is 90, it's just guaranteed that the largest angle is opposite the longest size, always. It's a property of triangles. So by invoking that, if this angle is greater than or equal to 90, there's only one triangle possible because the other fixed side has to be the longest side. It has to be therefore longer than this. And I'm just saying what I just hear through written out what I just told you. So only one shape is possible, and congruence is assured when the angle is greater than or equal to 90. So this ties in nicely to the conclusion before, that when one side's longer than the first side's longer than the second, only one shape is possible. The difference is that is possible when the angle is less than 90 degrees, but now we've shown it's automatically true when the angle is greater than or equal to 90. So to restate this in more general ways, we come up with two subclasses of angle side for which congruence is assured. First, side-side angle when the side not adjacent to the angle is as long or longer than the side that is adjacent to the angle. That then, if you have those conditions, then there's only one way to make the triangle. And side-side angle where angle is greater than or equal to 90, same thing. The second subcase applies automatically, or when the second subcase applies, the first one automatically does too, and it's the underlying cause for the second one. When this happens, this is sure to happen. Angle greater than or equal to 90, the first side that's not adjacent to the angle is going to be longer than the second. Now, one thing to watch out for is, in general, really, I'm sure you've seen this before in geometry, is which of the fixed sides is longer, and or whether the angle is less than, equal to, or greater than 90, based solely how it looks in the diagram, is risky. It's a useful hint, but you should be told that it's indeed the case, or use logic to confirm that that is the case before you rely on it. And finally, one last thing, hypotenuse leg. The previous two subcases are rarely considered, but this one is a subcase of the second subcase above. This one commonly is considered a rule of congruence. Why? Well, right angles are special and more likely to be told or be able to infer that an angle is 90 than any other interior angle. So this is often included in the rules, but include with an easier name, hypotenuse leg. Finally get to that congruence rule, which was mentioned at the beginning of the previous video, but never got to it. So how do we know how this relates to what we were just looking at? Hypotenuse and leg only apply to right triangles, so we know that the angle is 90 degrees. And we know from the name for the rule that there's a fixed angle. In this case, we even know the measure of the angle without including angle in the name because it's a right angle, so it's 90 degrees. By definition, the hypotenuse is always opposite the right angle, and it's the leg. And let's see, it's always opposite the right angle, and leg is so it's opposite the right angle, and then you've got the leg adjacent to the right angle by mentioning leg second. So you don't need angle in the name for the rule, to show that the fixed angle is in a triangle relative to where the fixed angle is in the triangle relative to the fixed sides. So the congruence rule, hypotenuse leg, is just an easier name for what you might otherwise call side-side angle, where angle equals 90 degrees, or side-side right angle. So these names show that this rule is actually not that different from the other congruent triangles rules. We just use a name that looks rather different because it makes it sound like it's, it makes it sound like it's different, but it's easier to say, easier to remember, easier to say. So that's where hypotenuse leg comes from. It comes from that case where you got a leg that turns out to be hypotenuse, and then a leg that's one of the, or sorry, a side that's the hypotenuse, and a side that's one of the legs, and then a right angle. And we saw in that situation where the first side mentioned is the longer one, then you're only going to get one possible triangle, and you've got assured congruence. So, thank you for watching, and I hope you found it interesting.